want to look at a more general process for an ideal gas called a polytropic process. And this is for an ideal gas only. Now that gives us a lot of capability, but we can't use it if we have saturated steam or any of that things we're using properties for. And what we've had so far, we had P equals C, T equals C, and V equals C, or specific volume is equal to a constant. So these are the three processes that we've had so far, but what we'd like is something more general. So a more general one is PV to the n is a constant, or P times specific volume to the n is a constant, where this is the polytropic exponent. So I have the polytropic exponent, and what I'm going to do, and if I look at this combination right here, so I have P1 V1 to the n is equal to P2 V2 to the n, and thus I have that P1 over P2 is equal to V2 over V1 to the n. And so I see they're inversely related. Now since this is an ideal gas, I can use the ideal gas equation of a state, PV equals mRT. So I could have P1 V1 is equal to mRT1, P2 V2 is equal to mRT2. And what I can do is I can take this information and put it in here and switch it around and get relationships between temperature and volume and temperature and pressure. And so I'm not going to do that on the board, I'm going to give you the results. You can see it, all the information in the text, of course. So we have that T2 over T1 is equal to P2 over P1 to the n minus 1 over n, and this is equal to V1 over V2 to the n minus 1. So I have a relationship between temperature and pressure, temperature and specific volume. I have the relationship between pressure and specific volume here. And now let's evaluate and see what the work would be for this process. So we'll look at a closed system. And we know that the work is equal to the integral of P dV. And I see that P, I have a relationship for P. P is equal to C to the B to the minus n. So now what we want to do is to be able to integrate that function. So we're going to integrate that, substitute in, and we have the work is equal to the integral from 1 to 2 of C, V to the minus n dV. And you know when you integrate, you add 1 to the exponent, you divide by that, and the C comes out, and we see, so I have, this is equal to C, V to the 1 minus n, evaluated between state 1 and state 2. And C is equal to P1 V1 to the n is equal to P2 V2 to the n. So I can pick whichever value I want for C, and when I integrate this, it'll turn out that in some instances it's better to have C be this or C be that. So work is equal to P2 V2 minus P1 V1 over 1 minus n. So when I substitute in and integrated that, and you'll notice that this is the ideal gas equation of state, mRT2, mRT1, and so we have here mR T2 minus T1 over 1 minus n. So this gives us the work for a polytropic process closed system. Delta U is equal to m C sub V T2 minus T1. Now, the following is not in the text. It's been brought back by popular demand because students went online and found out how to solve polytropic problems, and this was brought up. So, whereas I did this in the first edition of the book, I dropped it in terms of what I hoped would be clarity, but now it's being reinserted. So we're going to have something called the polytropic specific heat, which is totally made up. But what people like to do for polytropic process is they'd like to say that Q is equal to M C sub n T2 minus T1, where this was the polytropic specific heat. So that's the polytropic specific heat, and we're going to solve for this by applying the first law equation, and we know what work is, and we know what delta U is, and we can solve for C sub n. So we'll be able to come up with a function for that. So if I have Q is equal to delta U plus W, I have M C sub n delta T is equal to M C sub V delta T plus M R delta T over 1 minus n. And I know that R is equal to C sub P minus C sub V. So we had that from chapter 5. And so if I substitute all that stuff in, I'm going to get that C sub n. And you can do this, so you can give it a shot if you want. Do the algebra, it's not very hard. We'll see C sub n is equal to C sub P minus n C sub V over 1 minus n. So what we're able to do then is to solve for the heat directly. So we have a term for polytropic process, ideal gas, where I have an equation for Q, equation for W, an equation for delta U. So we can do a first law problem associated with that. Now let's do an example and see how this plays out. So in this case, we'll start with air in a piston cylinder. So we'll have air. We'll have 0.5 kilograms, 100 kPa, 300 K, and we're going to say that PV to the 1.6 is equal to a constant. So N is equal to 1.6, and P2 is going to be equal to 500 kPa. So what's happening is we're compressing, the air is being compressed, and the final pressure is 600, and we don't know what the final temperature is, but we'll find all that stuff out. So we have a closed system with the substance is an ideal gas. So I know I have PV equals MRT. We have the process is polytropic. And we know that Q is equal to delta U plus W. And we have the information to find all these terms directly if we want to. So using the relationship for T2, T2 is equal to T1 times P2 over P1 to the n minus 1 over n is equal to 300 times 500 over 100 to the 0.6 over 1.6, or we get that T2 is 548.6 degrees K. So I could solve for T2. And if you remember, we have all the equations need T2 in them, so we'll have what we need to solve for that. So then let's solve for delta U. So delta U is M C sub V delta T. Delta U is equal to 0.5 times 0.7176 times 548.6 minus 300. So we're going to have delta U is equal to plus 89.19 kilojoules. So we have what that is. The work is equal to mr T2 minus T1 over 1 minus n. So this is equal to 0.5 times r is 0.287 times delta t is 248.6 divided by 1 minus 1.6. And so we find that the work is equal to minus 59.45 kilojoules. And so, well, this is odd. The internal energy increased more than the work I put in. Well, maybe there was heat going in as well. So now let's see what Q is equal to. So Q is equal to m C sub n T2 minus T1. But now I have to solve for C sub n.